this one we'll do first is a 1-to-1 mapping. And here's a picture of it. A, B, C, and we'll say X, Y, Z. And let's put another one in, W. Let's say A goes to Y, C goes to Z, and we'll say B goes to W. Right, let's make it different. So in this example, FA equals Y, FB equals W, and FC equals Z. Now, why do we call this one 1-to-1? Because, well, it's for each element in the domain, it is mapped to only one unique element in the co-domain. So what it means is one element here gives you one element here, and it's different each time. Okay, that's what 1-to-1 means. One element back. If what goes in is different, what comes out is different. You never get the same answer twice. What is an example of a function like this? What function can you think of that always gives you a different answer? True. AX plus B. Good. Good. What else? No.
Plus and minus.
Yes. So what else then?
Y equal
no. Because if it's Y equals a number, you always get the same answer. What else?
AB.
AB. What the heck is that?
Like one number times another number.
Exponential. Good. Good. What else?
Log.
Yes. Good. What else?
Tangent.
No. Not tangent. Not sine. Not cos.
Yeah, tangent, right?
No. Tangent 0 and tangent pi are the same. Yeah, but it needs to be for everything. For everything. For everything. What about x cubed? X cubed. Oh, sorry. Did you write this down? This is the definition.
No.
Orange juice, chocolate pastry, and is orange juice in the cup?
Do I respect that?
I'm sorry, I don't understand chocolate pastry language.
Do I look bad?
No.
I didn't ask that again.
You need to do whatever Jerry's doing. He said he lost 10 kg.
I'm gaining
Oh, 5's better, okay. I thought you said 10. That would have been a big problem. What's your secret? To lose weight. What's your secret? Stress? Fall in love. Easy.
It's so easy.
That's a brilliant answer. That's a brilliant answer. Okay, did you write this down yet?
No.
No, okay, come on. I've started making my own coffee to save money. But I got these cups in the Euro shop. They're great, look at it. There's a little bird on it and everything. I'm happy.
How much to make your own coffee?
It's not as cheap as you think.
Me too, I'm thinking to...
60 cents? When you buy the coffee and the cup and everything. Okay. Continue. Okay.
Okay.
So, what would this graph look like if you were to plot it? Well, for a function to be one-to-one, let's draw something like, I don't know, like an x cubed. Okay, so for something to be one-to-one, it means it looks something like this. But of course, what exactly is it about this graph that makes it one-to-one? Well, there's a way you can check. What you do is you draw a horizontal line anywhere. Just pick somewhere randomly, like here. How many times does it cross the axis, the curve? Once. And then you draw a vertical line randomly. So we'll say here. How many times does it cross it? Once. Now, if this is true for every horizontal and vertical line, then we say it's one-to-one. So this is called the what you might call the horizontal and vertical line test. What you're looking for is to cross it once and to cross it once. Yeah? Can you draw this, please? This is what a one-to-one graph would look like. What they actually do is they would sometimes give you 4 graphs, and they would say which of these 4 graphs is one-to-one. Sometimes that's what they do, yeah. Or sometimes they don't give you a graph, and they just give you a function, and they ask you is it one-to-one or not. Now that's actually sometimes easy, but sometimes difficult to decide.
Okay, we know the function.
How can we know? We can know from the graph.
So if we have function, we should take graph.
Yeah. Yeah.
We can try.
Can I continue?
Yeah.
Okay, so the next one is come on. Many to one. Now, anybody want to have a guess at what they think this one might look like? So there's A, there's B, there's C, there's W, there's X, there's Y, and there's Z. Okay, so what might many to one look like?
FA equals X.
Okay, so we'll say FA equals X, okay?
FP equals 2.
Yes, that will do.
FA equals
Oh, we'll just say that. So what's happened in this graph, Sean? Why are you saying this is many to one? What reason? No, Sean. Why is this many to one? Because it is many to one.
FA equals FB equals X.
Yeah. It's because of this reason. It is many to one because there are an x1 and an x2 in the domain such that fx1 equals fx2. We have at least a pair of elements in the domain that have the same value when you put them in the function. So what would be an example of this, Lee?
X squared.
X squared. Give me the two example of two numbers that have the same value when you compute their f value.
3 minus 3.
Yeah, 3 and minus 3, for example. So, for example, if you have fx equals x squared, then f of 3 will be the same answer as f of minus 3. So we say it's many to 1.
Yeah.
Yeah? Got that? So, what about the graph? What might the graph look like?
Symmetric.
Say again? No, say it again, yeah? Symmetric. Symmetric, yeah, yeah. Symmetric would make it, but it doesn't have to be symmetric. Symmetric would make it many to 1, but if it's regular, if it's repeating, good. If it's symmetric, if it's regular, good. Things like this. So let's have a look at the graph. Can I scroll down, please? A little bit here. So what will the graph look like? It will look like this. Not like that. Hang on. This will do. This will do. Because what would happen is, for example, like here, this value of x and this value of x give you the same, and actually here as well, there's 3 that give you the same value. So how can you tell from the graph? Well, we use the line test. So if I draw a horizontal line, it's possible to make the horizontal line meet 1, 2, 3 times. If I draw a vertical line, it's only possible to make it meet once. So here there are many points, and here there is only 1 point. So we say it is many to 1, because horizontally there are many, and vertically though there's only 1.
Is that x cubed?
This is an x cubed graph, yeah.
It didn't look like 4.
No, it's cubed. Up, down, up.
So x cubed can be...
It can be both, actually. A plain x cubed by itself. But any x cubed that has an extra part, like an x squared or an x, could possibly be this shape, which would then make it the many to 1 type. Okay. Did you draw that?
Yes.
Yeah. Okay, so you can probably guess what's the next one.
Many to many.
No, before many to many.
1 to many.
1 to many. So, what's so special about 1 to many? A, B, C, X, Y, Z. Yeah. Yeah, there we go, that's it. A could go to X, A could go to Y, B could go to Z, and let's just put a, I don't know, omega here. Maybe C goes to omega. So this one is 1 to many. Why? Well, you can see that FA equals X, but also FB, FA also equals Y. So it is 1 to many because one element maps to 2 or more elements. So it's 1 to many because of what happens here. What might the graph look like for such a function? Not quite a circle. Doesn't have to be a circle.
It can be x squared plus
That's what he said. But not quite this, because that's not one to many. That's actually many to many.
It's 2 plus plus. Just x squared plus x cubed.
Describe the shape. What does the shape look like?
I don't know what
Go on, describe it. Go on, don't be shy. We're all friends. Describe the shape.
Oh, this kind of.
Yeah, that's it. The graph could be something like, let's say, like this. Because when we draw a horizontal line, how many times does it meet? Once. But when I draw a vertical line, many. So horizontally it's once, but vertically it's many. So this graph is 1 to many. This would be plus minus root x. Huh? Y equals 1? Fx equals 1? No, not this. No. No, I suppose that's true actually, because it does one. No. That is the f. This one here, fx equals 1, is many to 1, not 1 to many. Yeah. Because Jerry, here's the graph. So if I draw horizontally, it meets many times, and vertically it's once. Who the heck is calling me?
You have to go over the house right now.
It's not until 2 o'clock. No, it's not finished. I know what this is. People looking for maths help. Huh? Busy every day. I'm full.
Where's book? It's just in London. Where are my books?
This week is still next week. I've only broken my promise if it goes past Friday. It's only Monday morning. I have 5 days still.
Okay.
They stopped calling. It's good.
That's Wednesday, those are museum.
What?
That's June.
It's off now. Okay. Continue?
Yeah.
Yep. Alright, so what's the last one?
Many to many.
Ow. Yes.
Oh, goodness. Okay, many to many is the last one. And what is a function that's many to many?
Okay. Joker.
Yeah, but how would you describe it?
Circle.
Oh my, he just said that. I said, how would you describe it?
S square over 12 y square over b equals 1.
It's going to be a long week. But describe it like how I described these. Because it goes around. No, I'm not going to do it.
Because
Many to
one
many.
element,
What makes it many to many?
many elements
Oh.
are not going to many.
If it is both 1 to many and many to 1. Nice. If it's both. So A, B, C, X, Y, Z. So I need it to be 1 to many. Sean, you're distracting me. 1 to many. So A goes to X, Y, and many to 1. So I need another different point to go to one that I've already used. So I could just have C goes to Z and B goes to Y.
To Z.
No, that's fine too. That's fine too. So here one point goes to many, and here these ones, A and B, A and B both go to Y. So this one here. And then what would the graph look like? KJ, it would be a circle, or something like a circle. So, you know, could be something like this even. So here, something like a circle, it doesn't have to be a circle. So here it crosses many times, and here it crosses many times. So many to many. Yeah.
What is the function of the graph?
Huh?
What is the function of that?
You could have something like this, y squared equals plus minus root 1 minus x squared. That would make a circle. Yeah. Can I scroll down?
Yeah.
Now just to give you a little bit more vocabulary. So there is another name for one-to-one. Another name for that is called injective. Yes, that's another name for one-to-one. And if the range equals the codomain, so by that I mean if all the points in the codomain get used. So for example here all points are used, there isn't a point that has no value mapped to it. If everything in the codomain gets mapped onto, then we call this function surjective. Or the word we had last time is onto. And finally, bijective, which is injective and surjective. So it means every one goes to every one and nobody is missing over here. If it's one-to-one and everybody here is used up, then we say it's bijective. We need it to be one-to-one, so everybody gets one value only, but we need all the values to get mapped onto. Nobody's to be left out. That's the surjective. No, surjective just means there's nobody missing here. Surjective means everybody gets used, and injective means it's one-to-one. Bijective is a very important type of graph. In fact, it's the most important. And we'll see later this morning why it's the most important. Can I scroll down a bit? No. Well, what about to like here? So what does the graph look like for bijective? Everybody in the codomain is mapped onto. It's actually possible, KJ, for it to be bijective if there's values here which are not mapped but then they're not really part of the domain to begin with if they don't have a value that they're mapped to. So basically everybody's used. Can I scroll down? What does the graph look like? Well, firstly it's injective, which means it's one-to-one, so perhaps it goes something like this. Horizontally it meets once, and vertically it meets once. That makes it injective, but what makes it surjective on the graph? Each value gets used, so what does that mean on the graph? It means every single y value is used on the y-axis. Yeah, so in other words, the graph extends upwards and downwards to infinity. So here's an example. Is this one-to-one? Oh, it is.
Yes.
It is one-to-one. Because every horizontal value has at most 1, and every vertical value has at most 1, or none. Okay? But is it surjective? No, because not every y value is achieved. You've got a gap here, maybe from like 1 to 2, not achieved. So this one then is not surjective, which makes it not bijective. So not bijective. EX, bijective or not? EX, bijective or not? Come on, children, EX, bijective or not?
No.
Why?
Just guessing to us.
Fair enough. But have you got a real reason if you think about it?
Zero.
What about it? Give me a sentence with a verb. Correct. So it's not bijective. You cannot get negative values. Log x?
No.
Yes?
No.
It is bijective. Think about the graph. The graph is like this. Horizontally and vertically, how many times does it meet? Once and once. Is there any y values not achieved?
No.
No. Yeah, but that's not part of the domain. We're only using these values. What about x cubed? Bijective? X squared? X?
No.
X is bijective. The graph looks like this. Horizontally and vertically it meets once and it achieves all y values in the real numbers. Sin x, bijective or not? No, good. 1 over x.
No.
No.
Why not?
Can be zero.
Cannot be zero.
Yeah, but that's not the problem actually.
Yeah?
Yes, it is bijective.
It's not bijective.
No.
Is it 1-to-1?
Yeah.
No.
It is 1-to-1.
No.
It is 1-to-1. Yeah.
Yeah.
If it's not 1-to-1, you should be able to give me 2 x values that give me the same y value.
Oh.
So is it 1-to-1? Yeah. So why is it not bijective? Well, because it's not surjective. And why is it not surjective? What value does it not achieve? Yeah, you can't get y is 0.
Yes.
No, he said you can't get x is 0. That's not what makes it.
The y can be zero.
Yeah, y can't be 0. Is y is not bijective. But just because x can't be 0 doesn't make it true. For example, take log x. Can x be 0?
Yeah. No.
No, but it's still bijective.
Yeah.
Even though x can't be 0. It's still bijective. Because it achieves every y value, and horizontally and vertically it meets 1. Yeah? Let's do one more. Square root x. Square root x. Square root x.
No.
Why not? For what reason?
It's less than 1.
No. It is 1 to 1. Yeah.
1 to 1.
If it is not 1 to 1, remember you should give me two x values that make the same y value.
1 to 1.
It is 1 to many.
It's 1 to 1.
1 to 1, but
Square root
not
4.
subjective.
Correct. What values are missing?
Less than
Correct.
Huh?
Root x is 1
to 1.
to 1. If it's not, give me two values of x that make the same value. No, but if 1 to 1 means different x makes different y's, right? So if you're saying it is not 1 to 1, if this is your claim,
Zero can be.
But it can be less than 0.
huh? No?
Yeah. Many to 1 means you have different x, but very same one.
Yeah, many to 1.
The one.
No, you have many x.
It doesn't matter. If it's many to 1 or 1 to many, you still need to either give me two x values that make the same y value, or one x value that gives me two y values.
You can get positive ones.
Not true. Not true. So just to be clear,
How about I?
just to be clear, a lot of students make this mistake. They think that this is equal to this. This is false. This is equal to only this. Because that's the definition of square root. Square root is defined as the positive root. So you might be thinking, well, how come I get the plus and minus? Because the plus and minus, this is the mistake. Students think the plus and minus is because of the square root. It is not. It's because normally what happens is you have this. The plus minus here is not because of the square root, but because you were solving an equation.
Yeah.
So if I simply wrote down this, you must simply write down this. But if I wrote down this, then you can say plus or minus, because you're looking for all the answers that work.
Oh.
Okay, so square root is defined only as the positive root. This is the definition of root.
Yes.
Yeah. Okay? Let's have a look at a more difficult example now. So suppose I give you a cubic, something like, I don't know, y equals x cubed plus 3x squared minus 2x plus 1. Is this 1 to 1? Many to many? What type is this one?
Many to 1.
If we think about the graph, it should be many to 1. But not always, because if I give you this graph, you might think for the same reason this is many to 1, but in fact if you graph it, you get a graph like this, which is 1 to 1. So this gives us a little bit of a problem. How can we know which type it is? In other words, what could we do to figure out which situation I have? How might we figure this out?
The graph calculator.
The graph calculator would be extremely useful if you have that, but let's pretend only one student has it.
Turning point.
Very good, the turning point. What about it? Very good. If the cubic has only one turning point, then it's the 1 to 1 situation. But if it has two or more turning points, it's many to 1. So it depends on, in this case, what happens with the quadratic here.
Yeah.
Now, in fact, I don't even need to solve this. I just need to know how many roots there are.
Yeah.
B squared minus 4AC.
Four.
So it has two
Two. Roots.
turning points. Therefore, this
Minus one.
cubic is many to 1. It's all about the graph. The graph really can tell you what type you have. So a graphing calculator would be useful here, but you need to write something down. You can't like attach a screenshot of your... Yeah. Unless, can that print out graphs? Just...
I can check the answer.
You can check the answer, yeah.
I have a question.
Yeah.
You just 3x squared plus 6x minus 2 into x squared plus 3x minus 1.
Yeah, I divided by... Oh, sorry, that's wrong.
Doesn't make any sense.
I can't do that, sorry. Well, I think it's still the same. I divided by 2, but 2 doesn't go into 3.
Yeah.
No problem. It's still the same, I'm sure, I hope. B squared, yeah, because the minus makes the plus, plus 4AC, 8 plus 24, still positive. 2 roots, therefore,
Minus one.
yeah, the cubic is many to 1. Yeah. Now, before continuing, I just want to have a look at the questions I gave to see if there's anything I didn't cover. Let me just check here.
It is less than 0.
If what's less than 0? I don't know if that's possible. Can you get a cubic with no turning points? I don't know, Sean. I don't know if that's possible for a cubic.
Oh, it is possible.
Is it?
I swear.
Well, the simplest way is if you write down a cubic. Well, no, maybe it's possible actually. Let's test this out. Let's begin by writing down a quadratic which has no roots. X squared plus x. So that's b squared, which is 1, minus 4ac. So this quadratic has no roots. Yes? So if I integrate this, 1/3 x cubed plus 1/2 x squared plus x plus, let's just say, 1. Yeah, we'll just make it a number. Okay, so this cubic becomes this quadratic, which has no roots. So what type of cubic is that? Where it has no turning points. No turning points. Yeah, graph that bad boy. No, it has a graph, but it has no turning points. Let me open up my graph as well. You draw it?
Yeah, I agree.
Show me what wonderful thing you made. Let's see. Ah, that's not that exciting. By the way, Sean, it just looks like this. I guess that's a little bit different to this one, which goes like this maybe. You see here, it's flat, whereas here, it's not flat. Like here, the derivative maybe equals 1, whereas here the derivative equals 0. No? Here, I'll draw it here for you. Let me just check something here. 1/3 x cubed plus 1/2 x squared plus x plus 1. Everybody wants me.
Everybody like me.
Everybody. Come on, enter. What's wrong? Very famous. Oh, flip. Okay, let's graph this. Oh, come on. It has not.
Ask him.
Oh. Come on.
Well, you'll just have to trust me on it. Good. The graph has a slope instead of being flat, where the turning point may have been. Yeah. Okay. Thank you for trusting me. Right, let's have a look here. So, let me just check here. So the first one is you just have to say which of the 4 types it is. And you can draw the little graph to the side, but I think it might even be obvious from just looking at the functions. Like, for example, the first one, let's have a zoom in here. A goes to Z, A goes to X, B goes to Z, and B goes to X. Is it? Yes, you're right. It looks like it's this one here. A goes to Z and A goes to X. That definitely makes it one to many. But could it be many to many? So, for example, will I get a Z or an X again for a different value? B goes to Z and B goes to... Yeah, so the first one is many to many. Let me just check that. Sorry, scroll down. Many to many. Okay, and then the next one here, all you have to do is say, is it 1-to-1 or many to 1? Now, sometimes it's obvious, but sometimes you need a graph. Like, for example, here. Which is it, 1-to-1 or many to 1? 1-to-1. 1-to-1? This one? Many to 1. This one?
1-to-1.
This one's 1-to-1.
1-to-1.
This one is 1-to-1.
1-to-1.
Yeah. Because it has only one turning point. This one? No, this one's 1-to-1. This one? No. 1 to many. Oh, sorry. I mean to say many to 1.
Yeah.
Because there's 2 different values of x that will make the same denominator. So then 1 over the same value. It's kind of similar here. This one here, 1-to-1 or many to 1? 1-to-1. Because the power is 1-to-1 and the e is 1-to-1. So together they're still 1-to-1. Because remember, I'm saying, if you're saying it's many to 1, it means you can find 2 values of x that give you the same answer. What about this one, this log one here?
1-to-1.
It's kind of hard to tell here because it really depends on what happens with the quadratic. You see, the quadratic could have 2 values, true? So it might be many to 1. But what happens if the 2 values of the quadratic, one of them is positive and one of them is negative, which it could be? Then we're back to 1-to-1 because we can't use the negative value in the log anyways. So it really depends on where the turning point is here. If the turning point happens in the negative region, then it guarantees it's 1-to-1 from the graph. If it happens in the positive, then it's many to 1. So I think this one is worth doing as an example, and then I'll let you try some. y equals, or gx equals, log x squared minus 35x plus 304. It really depends on where the turning point is here. Let's look at where it is. That's 2x minus 35, yes? So that means x equals 35 over 2. So the answer is many to 1. Because this here, the quadratic will be symmetric here in the positive, which means there's two values of x I can put into my log that are the same. So for example, I don't know, if I use G16.5 and G18.5, I believe these will be the same, because it's 1 unit to the left and to the right of the turning point. So I think I'll get the same answer here. Could you type in log 16.5 and could you type in log 18.5, LM? Yeah. What? No, just log 16.5 and log 18.5. So log 18.5 is 2.9 and log 16.5 is 2.8. So it's not these two values that work. I think I might have to, for example, make this one a little bit bigger or something, but I'm sure I can get two values that will make the same value of y, but I don't think I have to do that because from the graph it's quite clear. Now if you really want to, we could find those two values.
So how come you know it is many to 1?
They're from my graph. But if you don't like the graph approach, guys, if you don't like how I did it with the graph, you could do it like this. You could just try and find x1 not equal to x2 so that gx1 equals gx2. We could try and find two values of x which are different but give us the same value of g. Let's see. Log x1 squared minus 35x1 plus 304 equals log x2 squared minus 35x2 plus 304. Okay, what can I do here to try and find the x1 and the x2? Well, first I should cancel log, right? So now I have x1 squared minus 35x1 equals x2 squared minus 35x2. Okay, let's take out the x1 here. I'm left with x1 minus 35. Let's take out the x2 here, and I'm left with x2 minus 35, right? Can I find two values? That is, can I find an x1 and an x2 which are different, but they give me the same answer here? Let's see. What about if I try x1 equals 0 and x2 equals 35? So what will I get on the left if I use this? 0. And what will I get on the right?
0.
And my x's different?
Yeah.
But I got the same value. So let's test it out. Let's go very back to the start. Let's calculate log 0. And then let's calculate the other one. What did I say? 35? 35 squared minus 35 squared plus 304. Yeah, you can see. You'll get log 304 for both. So in other words, g of 0 equals log 304 and g of 35 is log 304.
How do you draw the graph then?
The graph, I have no idea how the graph looks because it's log of a quadratic, so I can have a guess.
Oh.
What is the problem?
My program isn't working. Oh, sweet. That's funky. It has some, it's something weird like this. Why is there values forbidden here in the middle? Because that is when the quadratic is negative, which you can't use in the log. So that's why I have a piece missing in the middle. It's the part where the quadratic is a negative, and so the log is not defined, so we can't use it. So these questions are a little bit tricky. They really, really rely on your ability to visualize the graph and know how graphs work and calculus, and maybe put your knowledge together to figure out if it's one-to-one, many-to-one, or whatever. Yeah. In the exam, sometimes they give you something like this and ask you is it one-to-one or many-to-one, or sometimes they give you a graph. Obviously, when they give you a graph, that's much easier to do because you can just draw the lines to check. It's much harder to do if they give you this and ask you, because then you have to make the graph and think about it. Yeah. So question 2 is harder than question 1. Anything else just in question 2 here? Yeah, look at that one. That's and that one too. Tasty. Yeah, cost should be many-to-one. Because whatever value of x you find, you can keep moving until you get the same answer again because it repeats. So cost is obviously many-to-one. There's nothing actually to do. The ones which aren't obvious are the ones like the log, and this one here, the root of the quadratic. Again, something similar to the log. We can't use negative values, and it depends on if I can find 2 positive values that will have the same root. So for example, could I make this quadratic equal... no, actually, that's not... No, I think this should always be one-to-one, shouldn't it? Quadratic. No, because the quadratic is symmetric. We could get 2 values of x that make the same value of y, and so will have the same root. For example, maybe I can find 2 values of x that make this quadratic have the value of 9. Then what's the root of 9? It'll be 3 for both, yeah. So this one here, again, like the last one, you have to check out what's happening in the quadratic, where its turning point will be. Okay, very, very tricky lesson, very, very tricky lesson, and I believe it gets harder. Or does it? Let's just see the next one. Ah, no, the next one's a little bit of a break. It becomes easier. So why don't you take a break for 5 minutes and then we'll resume. How long do you need?
60.
What are you going to do for 10 minutes? Go to the canteen? Okay, well then get going. I'll give you 10 minutes. I'm not going anywhere because I'm too tired. Take a 10-minute nap?
No, I just want to put this back.